Hello and welcome back to Calculus 3. This is second part of 15.2. We need to deal with continuity for the day. So what we have is a part where we take the same ideas from Calculus 1, right? And go through the same but for multivariable function. So the first thing we do, we establish continuity at the point. Then we move from continuity at the point to continuity at all points we can find. And then take a look at some theorems and call it a day. So the first thing is the definition of continuity. The function goes to AB. Yeah, there's no end with number 3. 1 is equal to 2. Needs to give us the answer what F and A and B says. Yep, the projector is dead. So I can try and reconnect. Let's see. The selected projector is busy. Okay, let's see. So these are the 3 rules. They are exactly the same. They are exactly the same as the rules that you had for one-dimensional input. You just add f of x, right, with a, ignoring completely y's and b's. It's identical. So for function to be continuous at the point, they have to be the same point in order for it to work. Now, the best problems to consider, let's say problem 42 as an example. So divided by y to the 4 plus 2x square and 0. And this one is if 0, 0. So by looking at the problem statement, you see that the issue is at 0, 0. So your point A, B is the 0, 0 point. And you just run through all of the calculations. So number 1, what's f of 0, 0? Well, by definition, it's 0. That's the second line of your piecewise function. Next, we are supposed to find the limit of xy going to 0, 0. And we are going to look at, obviously, y to the 4 minus 2x squared divided by y to the 4 plus 2x squared. And see what we get in this case. So we are looking for a 0. And if this limit turns out to be 0, then we have 1 equal to 2, which fulfills the third requirement, and then we are done. So now we need to solve this limit. So let's we can't factor denominator. That's the bad part, because denominator has addition in it, right? We can't factor anything from any of the terms because they're different. And no square roots. So the question is, well, the only thing that we could try to do here, no, thanks. can we multiply this by y to the fourth minus 2x squared? If I multiply to create a perfect square on the bottom? Nah, that will not help either. Well, we have to turn this into two-dimensional problem first, right, with the one input, and then try L'Hopital, and that's doing paths. Y equals x along that line. Let's see, the trick is that we can only do a few of these. We can't really do all of them. This is a very evil limit for us to work with. So y equal mx. Let's see, because if this has no limit, then we're done. Y equals mx, so that's m to the fourth, x to the fourth, minus 2x squared, divided to m to the fourth, x to the fourth, plus 2x squared. So when we cancel out x squared, we get, so divide by x squared, we get m to the fourth x squared minus 2 divided by m to the fourth x squared plus 2. And when x is equal to 0, because x goes to 0, right? Well, there is here, limit x goes to 0 in front. We have the m terms die, and you just get -1. And you know what? This is good enough for us to break the whole thing. It's not continuous. It's not continuous because we just found a whole bunch of limits of this function, and the limits point to -1. So this limit is either -1 or something else, or does not exist. But look what we got for the function value. We got 0. So 2 equals to 1 equals to 2, which is a third in, right? The third requirement over here is that 1 equals to 2. But that's definitely going to be broken because number 2 over here is either a -1 if all the limits, right, you try all infinity of functions and they all point to -1, so it's -1. Or you try, let's say, quadratic function, you get a different number here. In that case, limit doesn't exist. So it's going to be broken either way. Let me explain one more time, but it's going to be more official because now I got up. In order for us to prove a continuity at the point, we have to have all three of these work. The 1 and 2 have to give you the same answer. So function value has to exist, and we see that from our piecewise function because on the bottom one says value is 0 if at 0, 0. So that line gives us number 1, and we know the answer is 0 because that's there by definition. Number 2 is the limit. None of the methods on the boundary work, so we go ahead and try to see if the limit doesn't exist with the 2 paths. Now I chose infinitely many paths over here because if the answer depends on m, limit doesn't exist. We learned that last class. So we went through calculation and we see that m's canceled because when x goes to 0, it kills these 2 terms. You just have -2 divided by 2, which is -1, and we're done, right? But that gives us the answer of -1. This one is 0, and this one is either -1 if all other functions align, or doesn't exist. It cannot be 0, right? Because you already have that some of the limits are -1. So there is no way that 3 is going to hold, no matter what 2 is, because 2 is not going to be 0. Definitely, because we already have that some of the limits are -1. So the 2 at best could be -1, but most likely does not exist. So if any of the three are broken, the whole continuity argument falls apart, and the function is not, not the argument falls apart, the function is not continuous. The argument is the theorem that holds. So you have to have all three of these give you, this has to, if this is 0, then this must be 0, and then 0 equals 0 in a third case. So this is either 0 equals does not exist, or 0 equals -1 at best. Both of those do not work here. So is definitely is not continuous at the point. So that's the way to check continuity at the point. You have to run all of these three. Now the next theorem is, or definition, actually not a theorem, is that global, let's write global continuity. So global continuity so the function f of xy is globally continuous if it is continuous at every point a, b in its domain. So some functions are continuous for some time, and then they stop being continuous, and then they might pick up continuity later. Just look at the surface of your desks. That's a surface. If you are to put a single sheet of paper on top of the desk, can you write? The answer is no, because you have that screen that it cuts in, and if you go on the pencil or a pen on a single sheet of paper, it will just punch through the paper. The function, which is just a plane, z equals 3 in this case, but it has this carved out. So it's not just z equals to 3, right? It has the piecewise elements in it to exclude the domain, which you can parametricize and make z value not be 3 at that point. Z value at that point is 0. So when you look at the surface of this desk, z equals 3, that's going to be on the first line for all points such that whatever the rectangle is, now you have to round it and do all of it. Well, actually you can use the edge of this, right? Because you're going to hit with a pen at the edge as well. So you see that the issue is, in that case, right, that function is continuous everywhere. It's going to be continuous here, it's going to be continuous in the middle. You can put the paper anywhere except along these edges. That's where the second part in that function definition is going to go on bottom says 0. So it's not continuous. Also, the edges are not continuous, because if you get to the edge, just fall off, right? The limit over here is 3, the limit on the floor is 0. So clearly the edge is not continuous because the number 2 is broken, right? The rule number 2, going from one end you get 0, going from the other end you get 3. They are not the same, so number 2 fails. So any of these points along the edge are not continuous points. So me saying that my desk is globally continuous, no, it's not. It has these holes for cables, it has the edge, it ends, right? So it's not globally continuous. Now it is piecewise continuous. Piecewise continuous means there is a chunk of the domain, right? And domain is a floor with all of the A-B points that give rise to all of these. Piecewise continuous means that there is a chunk of domain that has a continuous surface. Continuous surface doesn't mean flat. Continuous surface means whatever wavy surface you have, it doesn't matter. It just needs not to have these kind of sharp falls should not have an asymptote that everything kind of follows up and so on. So it has to be something like that. So global continuity, very simple, right? If the function is continuous at every point, then it's continuous globally. And for continuity, the same things you are used to breaking continuity will still break continuity. Anytime the denominator of the argument is 0, the denominator of the function is 0, anytime you have a function that it's discontinuous, you have 4 out of 6 trigonometric functions to be discontinuous on the entire domain. Only sine and cosine are continuous everywhere. You have 1 over x, well, 1 over y, 1 over xy. You can just make a lot of these discontinuities to show up in your calculations. So just be careful to check all of the points one by one. If you are thinking that there is a discontinuity, you have to run the 3 rules. And then the global continuity can only claim if you are certain that all of the points in the domain are continuous. None of them will make sense. Now, an example of the continuous, right? What would be an example of the continuous function? We have, so globally continuous. Let's say f of xy to be x squared plus 3y squared minus 6x plus 9, for instance. That's globally continuous. It's polynomial-like. It does not have any denominators, cannot have denominator equals 0. Polynomial-like structure, it does not have any vertical asymptotes or vertical planes to cut it or anything like that, so it looks all good. F of xy, let's say, e to the xy minus sine y plus 6. Again, we know that e to the x is continuous everywhere, and then e to the xy should be continuous everywhere. We also see that the sine is present. Sine has no vertical asymptote, so it's not going to create any vertical planes or anything for our function to go in a bad spot. F of xy, let's say 3 square root of x minus y. So this one is continuous on its domain. Yes, its domain is restricted. It's not all real numbers, right? In our previous 2 problems, domain was all real numbers. Now it's not. You can find what the domain is, but global continuity doesn't mean just continuous everywhere in the realm. It means it's continuous in a domain that the function has. So in this case, x minus y, that will give you a line y equals x. So anything above that line that produces positive values for the square root will, and the line itself, will have continuity, global continuity everywhere. So, and let's put another one, just because we can. F of xy is the ln of, let's say, x squared minus y plus 19, whatever, it doesn't matter. You can put whatever. This is, again, the domain for this exists. Once you find that domain, the rest is continuous everywhere. Again, no denominators, right? Now, if we get into not globally continuous, you might run into, let's say, a good old friend, f of xy equals to 1 over, let's say, xy squared, for instance. Now, let's just do xy. 1 over xy. Well, that's not going to be continuous because the function is undefined for 0, 0. function is undefined on actually entire x and entire y axis. Either one of those x or y's being 0 will give you the graph that is that excludes all of this. Let me see if I can quickly graph this for you. 1 over xy. So you should have this like cliff behavior at both x and y axis. And then at 0, 0 obviously fails as well. So it's going to look like a three-dimensional crazy version of 1 over x. Yes?
I have a quick question. So for 3 square root x minus y, if it's like if x is 1 and then y is 10, and it gives you -5, and it's under the square root.
That's what I said. You have to consider only the values that are allowed in the domain, which is why we find the domain. You find the domain, you will find y equals x, and then the line itself and everything above that line is going to be in the domain. Okay, let me see. Excellent. You gotta love when you have Mathematica present, right? So here is what the graph looks like on the 3D. So z equals 1 over xy, and just going to make it larger. Now, as I said, this software, guys, $1,000. It's free for you to download because you're students here. And if you have a software, so Wolfram Alpha will not let you do any of these things unless you pay, right, the subscription. But if you install the software, look at this. You can look this at any angle you want. So when you put it like this, you have your xy 1 over x, right? And then you can see which way it deals with the z-axis as you rotate. So I wrote in Mathematica plot 3D, and I just wrote z equals 1 over any parentheses x times y. And it gives, I think, it should show the input, right? Yeah, this is what I wrote. You can see it. Oh, it cuts off, actually, so you can't. The projector is not set up. Can you see it? Ah, it's right in this strip, right here. So this is what I typed in, plot 3D, and then z equals. And it gives you we can plot anything in Mathematica. So clearly not globally continuous, because if you are to walk on any of these surfaces, you're just going to fall off, right? So this piece over here is continuous forever. So that's what it means by piecewise continuous. You have 4 piecewise continuous pieces here, right? 4 continuous surfaces, but all together is not globally continuous because you have these tangent planes that cut, one through x-axis, one through y-axis, and then the functions bend to follow those planes without ever crossing or touching those planes. So there is no continuity because you have these, they're not vertical asymptotes, they're like asymptotic planes that the function approaches but never crosses. So yeah, the function has to inherit this. Now, again, it's not globally continuous. Now, if you take a look at your plot 3D for, let's go, plot 3D, z equals square root of, and what did we have, x minus y? We should see only one sheet, as you can see, only one sheet. They did give us only the real part over here. The red stuff is complex, so don't worry about the complex plane. And you can see, I hope you guys, you see x equals y, right? And that's the domain. Line y equals x, line y equals x is the domain. I don't have this turned properly, right? Let me see. Yeah, that's the y-axis. And oh, come on. Okay. No. Negative y need to go down. It's so hard to flip it the way I want it. Okay, now. So now all I need to do is to flip this top to be on the bottom. That's it. Good. Leave it. Oh no, that's good. This is it. This is what I need. Perfect. So now, as you can see, here positive 5 with negative 5, the x-axis, the y-axis going up, 0. So this line is y equals x. Y equals x for the domain. And you see that everything over here is below the line, not above the line. Anything below the line is giving you the real answer. And the red stuff is complex, right? So we don't care about the red stuff. We only care about this one. So it's like a, there's a bend like that, and it's going to go up. So now we can take a look from the side. So you can see your square root function, right? It works just fine. And everything on the yellow part, or orange, whatever the hell that is going to be continuous, right? And it's only one piece. The previous one had 4 pieces. So this is globally continuous, meaning continuous at every point. It does not have any vertical planes or anything like that cut it. Doesn't have any holes in it. It's just one sheet forever. One sheet forever. And it's very easy to obtain it, right? So you have a sheet, just a little bend over here, and you got yourself. Check all of your all at all points, and if you suspect some of the points, obviously they're not continuous, you can check them with the continuity rules, those 3 rules. If any fail, obviously not continuous. That's it. Bye.